Hello, hello, hello. Okay, so that was a latency test. That should be over now. Let us begin in a moment. Okay, then, hello anyone and everyone who is watching. Thank you for watching. If you enjoy this, make sure to please like and subscribe and hit the bell if you want to be notified of when we go live. If you have any questions throughout any of this, please feel free to insert in the chat. I would be happy to address it. Welcome to me, the first lecture of me, the Mathematically Expedient Modeling Exposition. This series will be focused on mathematical modeling, and the first part of the series is D's, differential equations made easy. So we're going to start very basically today with some simple ordinary differential equations. These are the fundamental building blocks in which a lot of continuous mathematical modeling occurs. So it's important to just lay a little bit of a groundwork so that if you ever need to go back and refer to, what should I know in terms of differential equations for the series, this is a good starting point. And with that, let us begin. So that's our main objective today. Also, if there are any technical issues with the stream, feel free to put that in the chat so that I'm aware. If you can't hear me, if you can't see me, well, you shouldn't see me, but just so that we can eliminate any technical issues. If I'm too loud, I'm too soft.
I tap out through the thingy.
No, that's a joke. I came really close to the mic on that one. But if there's something like that that's bothering you, please let me know as well. And with that, let us begin. So in mathematical modeling, there are two types of problems we often want to consider when using a differential equation. There are initial value problems and there are boundary value problems. Initial value problems specify, or IVPs, specify conditions at a single point, usually the starting point, and from which we can evolve the solution to a differential equation. There are also boundary value problems, which specify conditions at two or more points, typically at the end points of an interval. Generally speaking, initial conditions are not supremely important for solving a problem, though there are cases where, yes, it is important that we need to consider them. And though often they can be applied after obtaining a general solution to a problem. However, with boundary conditions, they often have to be considered from the start in how a problem is solved. And we'll go over examples of both of those right now, actually. We're going to start with the simplest initial value problem, and probably the simplest differential equation of interest. That is the the first order linear differential equation, dx dt equals lambda x of t, with an initial condition x of 0 equals x sub 0. In mathematical terms, like the calculus 1 way of describing it, this states that the rate of change is proportional to the current value. That proportionality constant is determined by lambda. It has the general solution of x of t equals x sub 0 times e to the lambda t. One can obtain this through a separation of variables and then an integration. You have a dx over x equals a lambda dt. You integrate both sides. You get a log x equals lambda t. You move the log around. There's a plus c involved in there, and that gets you an initial condition. And from there, you can solve the rest of the problem. If you're not familiar enough with calculus to understand this, this series probably isn't going to be for you, but you're still welcome to watch. Likewise, we have a fairly simple boundary value problem here. We have the second derivative of a function is proportional to is proportional to the function itself, and at the values 0 and pi, we specify that the function is equal to 0. And this is interesting, right? It basically says we're only concerned with the interval from 0 to pi. What happens beyond that usually is not of interest. And when we have that interval 0 to pi, we're saying that at the endpoints of this interval, this function has to be equal to 0. Now, what's important to know about this is that not all values of k will produce a non-trivial solution. Depending on the value of k, you could get 0 solutions everywhere. So if x equals 0, that will solve any version of this problem. So the second derivative of 0 is 0. You multiply that by k, it's still 0. 0 equals 0 is not a particularly interesting solution. It's a trivial solution, as we like to call it. The only time a non-trivial solution will exist is if k is equal to some positive integer n, in which case, with these boundary conditions, the solution to this problem is a times sine of nt for some constant a. And generally speaking, if we have a problem like this, boundary value problems tend to have a broader context in which they're being solved, which gives us the context for which we solve a. We're not going to address that here, but it exists. So if we want to solve more complicated differential equations, or if we want to solve more complicated linear differential equations, L of x equals 0, where L of x is this top row here, is this first centered equation. We have many derivatives of many orders with constant coefficients. We're going to essentially convert this into a polynomial, and this polynomial will be in the operator d equals d dt. This ODE then becomes a polynomial equation in D applied to the function x, and we're looking for where that equals 0. And this mirrors a matrix polynomial, right? The differential operator is a linear operator. That means if you have a sum going through the derivative, the sum is preserved. If you have a constant factor going through the derivative, that constant factor is preserved. That is what it means to be linear. And so, since it's a linear operator, it mirrors in many ways a matrix polynomial. And the solutions of that come from the eigenfunctions of the derivative. The eigenfunctions of the derivative, as we saw, or as we sort of saw in this problem, are the exponentials, e to the lambda t's, where e to the lambda t will have an eigenvalue of lambda. And so, if we treat this linear operator as if it were a matrix, though it is not technically a finite dimensional matrix, but if we treat it like a matrix, this characteristic polynomial, this piece of a term, when applied to itself, has to be equal 0. And this is connected to what is called the Cayley-Hamilton theorem out of linear algebra, where you generate this characteristic polynomial by means of a determinant of the matrix A minus lambda I, this becomes a polynomial, and the solutions to that polynomial tells you what values of lambda are the appropriate solutions for, or what are the appropriate values of lambda to generate solutions from. And so from this, we can build out the set e to the lambda t to form a basis of solutions. If we have repeated factors of lambda, we incorporate linear powers at t or other polynomial powers at t to build out this basis in a way to account for the multiplicity of the eigenvalue. So let's consider a crucial example, that is the oscillator. An oscillator, or just a more generic second order differential equation, a x double prime of t, b dx dt plus cx equals 0. Now the characteristic equation, that is if we say x is equal to e to the lambda t, will come out to be a lambda squared plus b lambda plus c equals 0. The values, the solutions of lambda will dictate the growth and decay rates and also the oscillation frequency. Now to solve this equation, this characteristic equation, we're going to use our good friend, the quadratic formula. X equals negative b plus or minus square root b squared minus 4ac divided by 2a. Y'all know the songs, y'all know the dances. I'm going to assume you know what the quadratic formula is. So if you take the real value of that lambda, that will dictate the growth and decay rates. And then the discriminant, that b squared minus 4ac term, will then dictate the overall behavior of this function. So if that discriminant is negative, that means that the eigenvalues are going to be complex. And this will produce an oscillation. And those oscillations are dictated by frequencies, which are the imaginary parts of that eigenvalue. If delta is positive, that means we're just going to have two solutions which grow and or decay as the algebra dictates. Growth will happen if the real part of lambda is positive and will decay if the real part of lambda is negative. If the discriminant is equal to 0, that means that b squared minus 4ac is equal to 0. We'll be left with solutions of the form e to the negative bt over 2a and t e to the negative b over 2a. That comes from that first term in the quadratic formula, negative b over 2a. The remaining terms have canceled out. And that t factor is what I was referring to earlier when I was discussing the multiplicity of that eigenvalue, in this case, negative b over 2a. Since we have multiplicity 2, we need two different terms to account for that. So here is a solid, concrete example of this. This is a underdamped oscillator. It is a prescribed frequency of, or prescribed omega of 2, and a zeta term, which sort of indicates our decay here, of 0.3. The characteristic is lambda squared plus 2 zeta omega lambda plus omega squared, which will have roots for these values anyway, of negative 0.6 plus or minus 1.92i. And this gives us a solution, e to the negative 6 of t times a cosine of 1.92t and b sine 1.92t. So what we see is that the decay rate of this, how fast the solution, the amplitude of the solution decays, is dictated by that real part, and how quickly it oscillates, the cosine and the sine terms, that is going to be dictated by the imaginary part. And this is an important feature to realize when discussing eigenvalue, the eigenvalues of a linear problem like this, when it comes to differential equations, because it's going to tell us how our solutions will grow and decay. If our solutions are growing, or they are decaying, or they are oscillating, this is often a very important tool that we need to know as mathematicians if we're going to analyze a system and understand what its behavior is. Okay. So, oscillators show up in a lot of different contexts. So I want to mention a few of them before we continue, because this is going to come up a lot as a sort of go-to example in this series as to what differential equations do. So if we have, so generically, the term A is an inertia. It is the oomph behind a system, for a given system. The B is some sort of restrictive term. That's sort of the to it. It's going to stop it, slow things down. It's basically the brake term, B for brake. And then C is a restorative force. It's basically it stores up energy or an equivalent quantity to be released and given over again to the inertia or to the restriction. So, two common examples that we will discuss is the mass spring system. So if we have a mass, that is assigned the value of A. That's the inertia of the system, or that describes the inertia of the system. B is often denoted in a mass spring system as gamma. There are some other values as well, or there's some other terms for it as well. Zeta is another one I've seen, like you saw in the previous slide. There's a bunch of similar type terms. That's the damper term. This can be achieved through like air resistance or a dashpot damper or some other friction within a mechanical system. And then C is typically the spring force. So if you have something that is stretching out, there's an elastic desire to restore itself to its normal equilibrium position. Likewise, in circuits, you have, for its inertia term, the inductance. So basically what happens with an inductance is you have a current flowing through, you have an electrical field that flows through a wire, and this generates a magnetic field. That magnetic field sort of pushes the electric field along. It's a form of inertia for that electric field. Similarly, you have the second term, B, is equal to R, which is often a resistance or conductance. It basically says, hey, you're flowing through a wire, you're bumping into protons or some other thing, or some other material. You need to slow down, or you are going to slow down because you're bouncing off all these electrons. And then in terms of a restoring force or something to restore an electric flow or an electric field, the C term is 1 over C, which those are different C's. 1 over C denotes a capacitance. Basically, if you have a capacitor or some other mechanism to basically store up electrical energy, that's where it happens. So another common technique for handling differential equations is through the use of substitutions. Now, this is one form of substitution. There are a bajillion out there. This is a Cauchy-Euler equation, and what makes it a Cauchy-Euler equation is you have a constant out front of each term, but then you will also have a multiplicative factor of the independent variable, in this case t, that is of the same order as its corresponding derivative. So our first term here is a(n)tn dnx dtn, and then at the very end you have at dx dt and plus a0 x. I should have written an x there. And what happens basically is the t's in front of the coefficients and the t's inside the derivatives. If you notice that the t is sort of on the bottom of the derivative, you can think of it not exactly like a fraction, but almost like a fraction. You have a tn over a tn, a t over t. Dimensionally, at least, those are going to cancel, so all the terms are going to have the same dimensions. It'll just be a times x of some form. And from that, because of that equidimensionality, we can make a substitution. So we have this example of x squared f prime of x, f prime minus f of x. And we make the substitution, s equals the log of x. And the reason why that works, and the reason why we can get away with using log of x is because there's no dependency is wrong. And we then define g of s is equal to f of x, but we're going to express f of x in terms of s instead. Using some chain rule formulas, we can relate f prime of x in terms of g prime of s. You can relate f double prime of x in terms of g primes and g double primes of s. And it simplifies to the equation you see at the bottom, g prime prime s minus gs equals 0. The solutions to that, using our previous tools, the characteristic polynomial there is lambda squared minus 1, which will have solutions lambda equals plus or minus 1. This will give us solutions of g of s equals e to the plus or minus s, and if we translate this back into f-land, solutions are going to be x to the power of plus or minus 1. So the solution will either be linear, it will have a linear term, and then it will have a 1 over x term. Let me just double check the chat, make sure there is nothing in there that I've missed. Okay. So another tool that we have in our belt to try to solve ordinary differential equations is the use of series solutions. So instead of just assuming that a solution comes in the form of e to the lambda t, which is a very useful guess, we can use a more generic power series expansion, as we see here. Jocelyn, what is the time in this place in India? It is 3:50. It's about the same time, except it is in the it's about 3 p.m. in my time zone. I'm outside. I'm in America right now, so opposite side of the world. I mean, if you're up this late, you don't have to watch now. If you want to go to sleep, that's totally fine. But anyway, thank you for watching. So yeah, we can use a power series to try to get a form of a solution. And if you plug this into a differential equation, what will happen in a lot of cases is you're going to often get these very crazy functions coming out. The most generic form of which is this, what we call a hypergeometric function here, this PFQ function. It will have P arguments A and Q arguments of B, and these describe the coefficients within this power series using the Ryzhik factorial. And it's called a Ryzhik factorial because a normal factorial or a falling factorial, you'll start with like n factorial equals n times n minus 1 times n minus 2 times n minus 3. The values are falling, right? n minus 1, n minus 2. But in this case, these factorials are rising. So we have a plus 1, a plus 2. So if you ever hear rising and falling factorials, that's how you can remember it. An example of such functions are the Bessel functions, which are the solutions to the Bessel equations, which have some non-integer power terms leading it, but the heart of it is going to be this hypergeometric series in terms of the value beta plus 1. And I and j, the difference between them is one of them. I believe the j uses plus 1/4 x squared, and I is minus 1/4 x minus squared. You clicked on the stream because you thought it would be a lesson on internet memes, not math. Well, I'm glad you're here watching this. Hopefully you're learning a little something. Whereas, yeah, no, I mean that was sort of deliberate on my part. I thought it would be funny to call something meme and see how many people would fall into my devious trap, because I am a scheming, evil person who wants to prowl upon people and make them learn math. Yeah, thank you anyway. Thank you again. So this is obviously very highfalutin. So let us see a concrete example. So we have the differential equation dx dt equals negative tx with an initial condition of x0 equals 1. We can assume a generic power series of the form x of t equals a n tn, summed up. And if we plug that into our differential equation and then go term by term, what we'll find is that we'll get this relation a n plus 1 is equal to negative a n minus 1 divided by n plus 1. From the equation, this tells us that we only need a couple of values to determine the full solution. So the first value we can determine is a 1. When t is equal to 0, the equation says that dx dt must then be equal to 0. And since the derivative corresponds to the a1 term, that tells us that a1 must be 0. And based on the parity of this, this an plus minus 1 relation, this tells us that all the odd terms must be 0. So we have an even function. And then we can determine the exact value of that by using the initial condition. And the initial condition tells us what the leading term of this equation is going to be. So this tells us that a sub 0 is going to be equal to 1, and then we can find that, and we can then use that recurrence formula to find a generic form of the terms we have here, or a generic form of the coefficients. And if we plug those coefficients in and we do a little bit of arranging, we will come to find that the solution is e to the negative t squared on 2, also known as the Gaussian, also known as the bell curve. There are a bunch of different names for this. 1 second. Sorry, there was something in my throat that I needed to clear, so you didn't want to hear that. Another form of series solutions will come up when we're talking about boundary value problems. Boundary value problems often yield a family of different eigenfunctions. These eigenfunctions will correspond to different eigenvalues. So this is the same problem that we were talking about earlier, very early in this lecture. We have this second derivative term with the 0 boundary conditions whose solutions were proportional to sine of k at t, where k was some natural number. Usually in a broader context, then you can take the different values at k. You have all these, you have sine of t, sine of 2t, sine of 3t. And for different values of ak, you can use it to build out an orthogonal, or these form an orthogonal basis, which then can be used to build out a Fourier series. For more complicated problems, you can represent a lot more functions using a Fourier series. And these ak values are going to depend on initial conditions or boundary, or not boundary, yes, boundary conditions, initial conditions, forcing terms for the problems. There's all sorts of things that can influence the values of these AKs. But if you want to build out a series solution, the eigenfunctions can also give you a way to do that. Another thing worth considering whenever you have a differential equation is what we can say sort of generically about a differential equation in terms of its solution. So if we have an initial value problem of this form, dx dt equals f of tx, with some initial condition, the solution will exist and will be unique in an interval about t0 if f is continuous and f satisfies the Lipschitz condition. That Lipschitz condition basically says that a finite difference between 2 points is going to be bounded by some constant k. This is known as the Picard-Lindelof theorem. This is just a common example that's fairly useful for ODEs specifically. A lot of differential equation research involves finding the uniqueness and existence properties for different systems. So it's not just Lipschitz. There's a bajillion other ways to describe different functions, different regularity conditions. A famous example of this is the Navier-Stokes equation, where there is a $1 million bounty out for someone who can prove or disprove. It's like the existence, uniqueness, and smoothness of the Navier-Stokes equations. This is one of those millennium problems, only one of which has been solved at this point. So there are still $6 million out there for someone who can solve it. Yeah, initial data is very important as well, as is the function space you're talking about. Probably the most important distinguisher, though, of solving a problem is the distinction between linear and nonlinear ODEs. If you have a linear ODE, all the terms involve a dependent variable and its derivatives are linear. So you'll have like x of t, dx dt. You can have all sorts of derivatives of x with respect to t, but you can't include terms like x squared, sine of x, products of x. Hello, Sachin. Hope I'm pronouncing that right. Yeah, linear solutions are nice because it gives us access to the tools of linear algebra, as we saw earlier when talking about the Cayley-Hamilton theorem as an example. Now, one important thing that I didn't mention at that point, or I don't think I emphasized well enough at that point, is that function spaces are not quite the same as spaces that you would deal with in a normal linear algebra class. In a linear algebra class, you learn about vector space. You typically learn about finite dimensional vector spaces, which are usually nice and behaved in various ways. However, function spaces tend to be a lot. They are a whole lot bigger, and because they are so much bigger, more precision is needed to accurately describe what is happening. However, that does not preclude the possibility of treating it like a finite dimensional space and then sort of going through it maybe right as a first pass. So if you wanted to model a function using a finite dimensional space, or if you wanted to treat it like a finite dimensional space, you could do that initially and then maybe go through a formal argument to check, oh, okay, so this part here with this like limit swapping, we can't do that because it's fully dimensional, or there's some argument that might break down in an infinite dimensional case. That's something you have to check for, but at least as a first pass, as a first model, treating a function space as a finite dimensional space is totally, it's a initially cromulent move. So if you're trying to model, that is fine. And that's what happened, and that's often what can happen, at least initially. And so it's worth mentioning that. Use the tools of linear algebra that you have available to yourself, and then realize how those tools may or may not work for your particular problem. If you have and that's why linear systems are so nice. There's a saying out there that basically the only math we really know as humanity is linear algebra, and that everything else is basically extensions of linear algebra to different applications. We turn this linear out, we take linear algebra, we apply it to this. We take linear algebra, we apply it to that. It's not perfectly true, but it's a good sentiment, at least. Nonlinear ODEs are those which are not linear. I've spent this past few minutes rambling about linear. So nonlinear are those that aren't. A very common example is the pendulum. I misspelled pendulum. Oh my goodness. It's. Oh no, I've forgotten how to. No, okay. The last E is a U. That is my mistake. Where basically x represents the angle of a pendulum, and dx dt is the acceleration term of that angle, the angular acceleration. Essentially, it basically pulls itself back and forth towards an equilibrium at zero. These are often much harder to solve analytically, but there are still tools with which we can analyze these. The tools are often just make it linear. So if you've taken a physics class and you've seen this equation before, you probably then heard your professor say something about using a small angle approximation, and that small angle approximation turns this into double x dot plus, or double dot x plus x equals 0, and then treat it as basically as an oscillator, as a linear oscillator. And that works for small angles and stuff like that. And there is like an analytic solution for the pendulum equation that involves like, I think it's like Jacobi elliptic functions. Don't quote me on that. It's one of those fancy functions out there. Can be used, are basically used and defined basically to try to solve this particular equation. But broadly speaking, we don't have solutions to most nonlinear ODEs, but we still treat it. We can still often analyze them using some linearity. A future lecture will go into linear stability analysis for a nonlinear system. So if you want to see that, make sure to subscribe and hit the bell so that you know when we go live. I feel like I have to include that somewhere in here. And then I think our final slide is an example of a solvable nonlinear PDE, but that comes basically by if you have a nonlinear equation of the form g over t, g of t over f of x, you can move the x and the g to separate sides to get an integral equation. So f of x dx, a g of t dt, you integrate, and then you solve for x. So in this case, we have a logistic growth equation. This is commonly used to model the spread of disease. And so then you can move the x terms over to the dx. You move the dt term over to the r. And what you get is a solution of the form kx or k e to the rt over k plus e to the rt. There's some constants omitted in that statement, but and that can be solved using a separation or no, not separation of variables. That was the first step. Partial fraction expansion in the integral. This is a separable equation. This doesn't universally work. The integrals themselves can become very hard, and then trying to solve f of the integral f of x and equals g of t and solving for x is also very difficult. But if you can find a solution like this, take the solution. It's really cool. I have my math book by Ryzhik book open by my side. I get what it's trying to say while watching you. Yeah. What are you trying to get, Jayton? Garius. Yeah, because I'm basically done with my slide stuff. Yeah. Have some question. I do have tools available to maybe take a crack at what you're trying to understand. Kreisig. Oh, you can now understand what the book is saying. Okay. What was the book? I'm just curious what the book was saying. Was it talking about the linearity part, or was it the, or what? I'm just sort of curious what I helped to resolve here. Section on series. Okay. Yeah, no, series are trying to understand a series solution to an ODE is, it's a useful tool for sure. However, it can very quickly turn into looking up and studying sort of arcane applications of it. There are a pair of books out there called, the first one is a little more famous. It's called Abramowitz and Stegan. Actually, let me make a note. The first one is called Abramowitz and Stegan. That book was sort of, I believe it was basically transcribed onto the NIST website. On what's called the Digital Library of Mathematical Functions. I just need to make a note to put that on the show notes. And then the other one was called Gradshteyn and Ryzhik. Gradshteyn and Ryzhik. I forget the exact spelling off the top of my head. And both of these books basically will go in and talk about all these functions that were cooked, these functions that are series solutions to different differential equations over the years. These were particularly popular before the advent of computing and numerical solutions to ODEs and PDEs, because you sort of had to solve them by hand because you didn't have those numerical methods available, or you didn't have the computing power available to use numerical methods reliably. And so, if you read those books, I basically treat you like you're some sort of wizard, basically. Just standing in your, sitting in your tower with your book, your tomes of integrals, in series relations. They're pretty cool. I'll definitely have to share those references in the in the show notes. And with that, though, I plan to go about half an hour, and half an hour has elapsed. So over half an hour has elapsed. So I'd like to thank you all for watching. If you are watching this afterwards, make sure to like and subscribe and all that good stuff. If you like this video, then like this video. I'm not sure when exactly the next stream is going to be, but I do know that the topic is going to be different time derivatives, right? Modeling often starts with like, oh, we have just ddt or something like that. But there's also other time derivatives. So this is the material derivative. There's a few other similar ideas in it that I'm going to be talking about the distinctions of, and it'll be maybe kind of useful. So who knows? Anyway, thank you for watching. Have a good day. Take care. If you like this video, then like this video.